Today the topic of our lecture is example 10.5. Here we are given that a music helical wire spring should be designed for infinite life, and the load that will be applied on this spring will be from 5 pounds to 20 pounds. 5 pounds will be the minimum force and 20 pounds will be the maximum force, and the frequency is 5 hertz. And when you apply 5-pound force, the deflection will be 0.5, and as you increase the load, the deflection in the spring will increase such that at 20 lbf force the deflection is 2 inches, and the solid length of the spring should be equal to 1 inches, and the free length should not be more than 4 inches. And you, the spring maker, have only these sizes of the wire diameter. So we are required to design this spring, and in the design what you will have to do is to select this wire diameter for these values, and all other necessities are given to you. Based on these necessities you will have to find these values. That is what is called design of the spring. So let's say you take wire diameter 0.112 inches, which is this one. You will have to take some decision, as you are given that the material is music wire. So in the music wire, this is the table 10.4, for which in this table the value of M and A are given. M is 0.145 and A is 201. So these values will be used later on here. This relative cost also be used. Here if you see, the value of G is 11.75 psi. This value is taken from another table. Now this is the decisions that you will have to make, means whether you want to make a peened spring or unpeened spring. The strength of the peened will be greater than the unpeened. So here we have decided that our spring will be unpeened. Then we are going to make another decision, which is about the ends of the spring. We want to have a spring with the squared and ground ends. The zeta value for this spring, we want it to be 0.15. The set will be as wound condition, and then we have the fatigue factor of safety 1.5. Using sine zimmerli fatigue failure criteria, and this spring should not buckle, we will use the spring without any rod or a hole. The decision variable is wire diameter D. If you change the wire diameter D, all other quantities will get changed. So first of all, let's find out the alternating force, which is equal to F max minus F minimum divided by 2. So 20 minus 5 divided by 2 will give you 7.5, and F mean is equal to F max plus F minimum divided by 2. 20 plus 5 divided by 2 will give you 12.5. And then after that we want to find out the spring rate K. F is equal to Kx or Ky. So if you put F max instead of F, then you will have to put Y max instead of Y. So rearranging for the K, it will give you K is equal to F max divided by Y max. F max is 20 and Y max is 2, so it will give you 10. And similarly, if you put F minimum divided by Y minimum, it will give you the same result, means 5 divided by 0.2 will give you 10. So this is the value of the K. Then let's talk about formulas that will be used for the required quantities for the design. Mean coil diameter is equal to C into D, and C is given by this formula. Till now we were calculating C from the formula, that is mean coil diameter divided by wire diameter, but as you know that we have only wire diameter, we don't have a spring mean diameter. So when you don't have spring mean diameter, then you can find out the value of C from this formula. You know that tau S, which is the stress produced in the spring when you bring that spring to the solid length, and if you want that spring to be solid safe at that stress, then the formula for that is equal to SSY divided by NS. And as you know that this tau S is also equal to KB into 8FS into mean coil diameter divided by pi d cube, and this K is equal to 4C plus 2 divided by 4C minus 3, and here this Fs is equal to 1 plus zeta into F max. This zeta is 0.15. You take these two equal to each other and take this one as alpha, and here this quantity into beta. So you have the relation that is alpha is equal to 4C plus 2 divided by 4C minus 3 multiplied by beta into C. Now what you will have to do is to rearrange this formula for this C. When you rearrange this formula for the C, you will get this equation. But here you know that this formula is for the static load. We want this design for the dynamic load. So for that, when you replace this SSY by SSE, then you must replace this NS with NF. This will be equal to alternating stress produced in the spring. So if this is the alternating stress, then here instead of Fs you will have to put Fa. So instead of this term you will have Fa. Now alpha will be equal to SSE divided by NF, and beta will be equal to 8 Fa divided by pi d square. So instead of this term you will have Fa. So this is how you will have to calculate the value of C. SSY can be found from this equation, and here SUT can be found from this equation. A and M value have already been taken from table 10.4, and here the internal diameter can be found from this mean coil diameter minus wire diameter, and external diameter can be found by this equation, which is mean coil diameter plus wire diameter. And we have already talked about C value, and then NA value can be found from this equation, which is wire diameter to the power 4 into G divided by 8 into mean coil diameter cube into K. So this is how we can find out NA. Then LS can be found from this equation, D into NT. Then we can find free length from this equation, that is equal to LS plus YS. YS is the deflection when you force this spring from the free length such that you bring it to closure, means to solid height. Then if you add this deflection with the solid height, it will give you the free length. And L critical is actually used to find out whether the spring will buckle or not. This is the formula for that. So if you want that your spring should not buckle, so your length should be less than 2.63 into mean coil diameter divided by alpha, and alpha will be taken from the table, and that will be based on the In's condition. And F can be found from this equation, and S can be found from this equation. F can be found from this equation, and form can be found from this equation. So let's find out SUT by putting A equals to 201 and wire diameter 0.112 and M value 0.145. So it will give you 276.12 kpsi, and SU can be found from this equation. So when you put SUT equal to 276.1, it will give you 185 kpsi. And if you put SUT in the SSY equation, it will give you 4.2 kpsi. Now let's find out alpha beta to find out the value of the C. So as I told you earlier that here for the dynamic case, alpha will be equal to SSE divided by NF. And as you know that using sine failure criteria and taking the zimmerli data, you know that for the sine failure criteria, SSI is equal to SSE and SSM is ignored, or it is taken to be equal to 0, and you know that it can be taken to be 0 for a type of dynamic load where sigma max is equal to the sigma minimum. So SSE is equal to 35, alpha is equal to SSE divided by NF, and as I told you earlier in the decision part that factor of safety should be equal to 1.5. So putting these values, it will give you alpha is equal to 23.33 3 kilo psi. Now you can find out the beta value as well. For that, if A is 7.5 and D is 0.112, so when you put these values, it will give you 1.5225 kilo psi. Now you know the values of alpha and beta, and you will have to put these values in this formula. It will give you 14.005. So the value of this C is 14.005. When you multiply 0.112 with the 14.005, it will give you 1.569 inches. That will be mean coil diameter, and then internal diameter will be equal to 1.457 when you subtract this wire diameter from the mean coil diameter. And if you add mean coil diameter with the wire diameter, it will give you 1.68. So we have found these values. This is the formula for the number of active coils of the spring, for which you know that G value is required, and the G value can be found from table 10.5. And here if you see our diameter was 0.112, 0.112 is in this range, so your value for the G will be this one. Putting the value of G to be equal to 11.75, and this wire diameter is 0.112, and this K is 10, while the mean coil diameter is 1.569, so it will give you 5.98 pound per inch. In fact, there is no unit with the to find out the solid length and free length. You can use this formula. Since we told you that our design will be based on squared and ground, and so for that, this is the total number of active coils. So if you add 2 over here, it will give you 7.98 turns. And if you multiply 0.112 with the total number of active coil, which is 7.98, it will give you solid length. So this is the formula for total active coils, and this is for the solid length. Total active coil is 7.98 and solid length is 0.894 inches. Free length, as I told you, is equal to ls plus ys. You know that ls is this one, and you don't know about the ys. So this ys can be found from this. Now you need to have this fs. So fs can be found from this equation, that is 1 plus zeta into f max. Zeta is 0.15 and f max is 20 lbf. So 1 plus 0.15 will give you 1.15, and 2 f max is 20, so it will give you 23 lbf. So putting this 23 over here, this k is 10, this ls is 0.894, so putting these values, that will give you 3.194 inches. That is free length. After that, we can also find out the ys as well. If you see, L naught is equal to ls plus ys. So if you rearrange it for ys, it will be equal to L naught minus ls. That is also equal to fs divided by ks. So ys will be 2.3. And to find out L critical, you should multiply this mean coil diameter with 2.63 and divide it by alpha, and this alpha value can be found from table 10.2. We want this spring to be supported between flat parallel surfaces, so for that alpha value is 0.5. So when you put 0.5 value, it will give you 8.253. This is the L critical value. Now since your length is 3.194, which is less than 8.253, so spring will not buckle. And kb can be found from this equation, which is equal to 4c plus 2 divided by 4c minus 3. It will give you 1.094 by putting the value of c to be equal to 14.005. Now after that, tau a can be found from this equation, which is equal to kb into 8fa into mean coil diameter divided by pi into wire diameter cube. If a is 7.5, previously we have calculated it, and mean coil diameter is 1.569 and wire diameter is 0.112, so it will give you 23.334. And tau m can be found from the same equation, but you will have to replace fa with the fm, and fm was 12.5. So putting this value, it will give you 38.89 kPsi. Now if you want to find out the tau s, that is the stress produced in the spring at solid length, as you know that tau s is equal to fs divided by a, and similarly tau a is equal to fa divided by this. Now if you divide this first equation with the second, so you will get this. Here this a can be cancelled out with each other, so you will get tau s divided by tau a is equal to fs divided by fa. Now if you want to rearrange this equation for the tau s, you will have to bring this tau a to the other side of the equality. For that, you will have to multiply it on both sides, so tau a will come over here, and tau s is equal to fs divided by fa into tau a. Now if you put the values, it will give you 7.156. Now from these tau a, tau m and tau s values, you can find out whether the spring will be safe or not, and what is the design factor, what is this solid safety. So factor of safety is equal to SSR divided by tau m, and that is equal to 1.5, because SSR from the zimmerli data is 35 using the sine criteria. And if you want to check whether spring is solid safe or not, for that you will have to divide SSR with the tau s. So when you put these values, it will give you 1.74. And if you want to find out the frequency, natural frequency, for that you will need this specific weight of this spring W, which is given by this equation, that is pi square d square into mean called diameter into Na into gamma. Gamma is 0.284 for the music wire. So putting all the values that we have calculated along with the gamma value, that is 0.284 for the music wire, it will give you 0.0825 pounds. And you know that frequency is equal to half of under root k into g divided by w. You know the value of k, that is 10, and the value of g, that is 10 meter per second square or 9.8 meter per second square, and when you convert it into feet per second square, it will become 386 feet per second square. So putting these values, it will give you 108 hertz. Now after that, you can find out the form from this equation. The relative cost was taken from the table. So putting these values, it will give you minus 1.01. Now since you have calculated all these required things using the given equations, but you know that you have calculated these values only for 0.112 wire diameter. Now if you want to design a spring based on 0.105 wire diameter, then you will have to use the same procedure. First of all, you will have to find out this C. So for that C, what you will have to do is to change the value of this D. Here in the first case it was 0.112. So when you put another value, it will give you another value of beta. So putting another value of beta, you will get another value of the C. So your C value will get changed. Similarly, since this is going to change, this is going to change, this will be the same, and this may also be the same, but these two values will get changed. So because of that, Na will also change, this Ls will also change because Nt is going to change, and Nt is actually going to change because of this Na. So using the same procedure, you will have to find these values for 0.105. So we have obtained these values. Similarly for 0.095 we will get these values, and so on. Now since you have completed the table for all the given wire diameters, so now what you will have to do is to check this table based on certain criteria. One criteria was given by the customer, that was this criteria, that Ls should be less than or equal to 1, L0 should be less than or equal to 4, and natural frequency should be greater than 5, because the forcing frequency was 5 Hz. These are the general criteria that should also be met. The values are nearer to these equation, then you can use those designs. So for that, first of all, if you check this first case, here in this case your Ls is less than 1, so for the first case this is okay, and L0 is also less than 4, so this is also okay, and natural frequency is 108, which is greater than this. So for the first case, these equations are satisfied. Now if you look over to these equations, so an A value should be between 3 and 15, so it is okay, and C value should be between 4 and 12, it is 14, it is not met, but still it can be used. L critical, you can see, is greater than the spring length, that is 3.195, so it is greater, so this is also met. So in the first case, if you see, only this C criteria is not met, but still this can be used as a design. But if you see for the others, these criteria are not met. For example, for this Ls is greater than 1, so as you see, this is greater than 1, but your customer told you that it should be less than 1, so you come across this result, leave your calculation over there for this spring, jump to the next, and for that you see again it is greater than 1, jump to the next one, for that the Ls value is again greater than 1. If you see for all other designs, your this equation is not met, so all other designs are not suitable for your customer.